So now let us see two important theorems related to distance of chord from the circle. We are still on the same chapter, circle itself. Okay, so the first theorem, I've already written it for you. First theorem states that equal chords of a circle or congruent circles. What do you mean by congruent circles? Circles having equal radii. So, equal chords of a circle are equidistant from the center, right? Equal chords of a circle are equidistant from the center. Mathematically, if suppose I have a circle, this O is the center, I have two chords AB and CD which are at a distance of OM and ON from the center, and if it is given that AB is equal to CD, that is both the chords have equal length, then this implies that OM is equal to ON, that is the distance of the chord AB from the center is same as the distance of the chord CD from the center. Now let us see why, how and how to prove this. Say now what I'll do, I'll join as usual O with C, O with D, O with B and O with A. Can I say that triangle AOB is congruent to triangle COD? Will they be? Yes, they should be, because first thing, it is given that AB is equal to CD. Second, this is equal to this is equal to this, all being the radius of the same circle. So by SSS congruency, both the triangles are congruent to each other. If they are congruent, now you know that congruent triangles have equal area, right? If two triangles are congruent, it means that they will have equal area. We will use this concept for proving that OM is equal to ON. Now, if I try to write down the areas of triangle AOB, so using this, I can say area of triangle AOB is same as area of triangle COD. This implies half into base of AB, AO triangle AOB is AB, into height is OM is same as half into base CD of triangle COD into height ON. Half of cancelled. Now AB is equal to CD, both are equal chords, it is given, so they cancel out each other. So finally we have OM is equal to ON. Hence the distance of the chord, this is perpendicular, yeah, distance of the chord CD is same as distance of the chord AB, hence proved. Second theorem is basically the converse of this theorem, which states that chords equidistant from the center of a circle are equal in length. That is, if it is given that OM is equal to ON, that is this distance OM is equal to ON, then the chords are equal in length. That is, AB will be equal to CD. How to prove it? Let us see. I'll join OC, OD, OB and OA. Now in triangles AOM and triangle CON, right, that is this triangle and this triangle, I can say that AO is equal to OC, right, radius of the same circle, right. Since both the chords are equidistant, it is given that is if OM is equal to ON, so I can write OM is equal to ON given. And third thing, angle OMA is equal to angle ONC, 90 degrees, right? So by RHS congruency, I can say that triangle AOM is congruent to triangle CON by RHS congruence criteria. And if both the triangles are congruent, now I can write AM is equal to CN. Why? CPCT, corresponding parts of congruent triangles. If AM is equal to CN, this implies 2 times AM is equal to 2 times CN, which gives us the result AB is equal to CD. Why 2 times AM is AB? Because you know that the perpendicular drawn from the center to the chord bisects the chord. That you can easily understand the proof of this theorem when you'll watch the previous video. So we'll use the same concept here, that is 2 times CM is equal to AB and 2 times CN is equal to CD. Hence AB is equal to CD, hence this theorem is also proved.